If you've ever had a package show up, completely crushed, or if you've ever just wondered why shipping costs seem to be constantly going up, well, there's this kind of hidden villain in the supply chain. We're talking about deadweight, specifically the heavy, often pretty inefficient packaging, like the logistics crate.
It really is. It's like a silent tax on the entire global economy. I mean, logistics companies are always fighting this three-front war. They're
Right.
trying to cut costs, improve efficiency, and, of course, lower their carbon footprint. And dead weight, just unnecessary material, is the enemy of all three of those things.
Every single pound counts.
Every pound. It means more fuel burned on a truck, on a ship, on a plane. It all adds up.
So the mission, at least in theory, seems simple. You just make the crate lighter, but you can't compromise on strength.
But that's a classic engineering paradox, isn't it?
It is. How do you lose all that mass, but keep the structural integrity you need to survive, a really rough journey? Well, today we're diving into the technology stack that's actually answering that question. It's a really powerful combination of topology optimization, artificial intelligence, and 3D printing.
And this combination, this convergence, it's fundamentally rewriting the rules for the supply chain. We're going to show you how AI can design what is, in theory, the perfect structure.
And then how 3D printing is really the only way you can actually build it.
Exactly. This deep dive is your shortcut to understanding why the humble logistics crate is kind of secretly ground zero for the future of industrial design.
Okay, so let's start with the theoretical foundation here, which is topology optimization, or TO.
Right.
For anyone listening who hasn't really come across this concept before, I mean, it sounds incredibly complex, but at its heart, it's really just about structural efficiency.
It is, yeah. You can think of it as a computational mandate for material efficiency. So topology optimization is this advanced mathematical technique where you define a space, say the total volume of a standard crate,
Okay.
and then you basically tell the software, maximize the performance of this structure, but use the absolute minimum amount of material to do it.
Ah, so that's the key difference then. It's not just an engineer manually, trimming corners or making the walls a bit thinner.
No, no, no.
Tuo's asking, on a structural level, where does the load actually go?
Yeah.
And what material can we just get rid of without causing a failure?
Precisely. The best analogy is a bone. A bone isn't a solid block of material.
Right. It's got that internal structure.
Exactly. It's reinforced with these intricate internal structures only where the stress is highest. Tuha algorithms work in the exact same way. They run, millions of simulations to just carve out mass, showing an engineer where the material is basically just decorative weight and where it's absolutely essential to carry a load.
So the result, in theory, is this incredibly lightweight structure that performs just as well as, or maybe even better than, its solid, heavy counterpart.
That's the goal.
And for logistics, saving even a few kilograms per crate has to be an exponential saving.
Oh, it adds up so fast. Just imagine stacking thousands of these on a single container ship or filling a cargo plane. If you can cut the packaging weight by, say, 30%, you suddenly have more payload available for the actual goods.
Or you just slash your fuel costs.
Or you slash your fuel costs across the entire trip. Reducing that dead weight is the single most direct way to impact both transportation costs and energy consumption.
Okay, so topology optimization as a concept has been around for decades. But it used to be this really resource-intensive process. You'd have high-level engineers running these huge simulations for weeks, maybe months.
That's right.
This is where AI comes in to, turbocharge the whole thing. How does machine learning take this concept and just accelerate it to the next level?
Well, the problem with the traditional approach with TO is that you still needed an engineer to set all the initial constraints and then manually interpret these really complex results and then run more iterations.
A lot of trial and error.
A lot of trial and error. AI changes the game by using machine learning algorithms that can analyze these vast dynamic data sets all at the same time.
Can you give us some examples? What kind of data is the AI analyzing that a human engineer would just struggle to process?
Sure. It goes way beyond just knowing the maximum weight a crate has to hold. The AI looks at historical failure data, yes, but more importantly, it's feeding in real-world operational constraints.
Like what?
Things like thermal expansion data, vibration frequencies you'd encounter on specific truck routes, historical stress cycles, even simulated fatigue from being loaded and unloaded thousands of times.
So the AI isn't just optimizing for pure strength. It's optimizing for strength and all the dynamic, messy conditions of the global supply chain.
Exactly right. The system is balancing these incredibly complex trade-offs. It might figure out that to handle high-frequency vibrations from a truck, one area needs to be solid, but to handle high heat in a desert, that same area needs a specific, more porous internal lattice to dissipate that heat.
And the AI figures out the perfect balance.
It suggests the most efficient geometric solution based on all of these competing data-driven insights.
It sounds like a problem that just explodes way beyond what a human could intuitively solve. I
Mhm.
mean, the machine is defining a geometry that a person probably wouldn't even think of
Right.
because they're limited by what they know can be, traditionally manufactured.
You've hit on the central barrier right there. The system balances strength against material constraints, and the designs it generates, these ideal, mathematically perfect shapes, they're often breathtakingly complex. They have these organic-looking, intricate internal lattice structures.
Impossible to make normally,
A human engineer designing for a traditional process would start way before that point because they know that shape is just impossible to mill or to mold.
which brings us to the perfect marriage. Optimization meets manufacturing. You can have the most efficient design in the world, but if you can't actually build it economically, it's just a rendering on a screen.
So why does topology optimization need 3D printing?
Because of that exact complexity you mentioned, traditional manufacturing methods are subtractive.
Right. You start with a block and cut stuff away.
You start with a block of material and you cut away what you don't need. And that makes creating those complex internal channels and customized lattices either physically impossible or just financially ruinous because of the material waste and the machine time.
But 3D printing is additive. It only puts material exactly where the AI says it's needed. That's the key technical breakthrough. It builds the object layer by layer, which allows for these incredibly intricate, customized hollow or cellular structures that the TO algorithm designed. Once that optimal design is ready, it's printed using lightweight, super durable materials, things like metal alloys or specialized composite plastics. And these materials, guided by that optimized shape, make sure the crate is tough enough to handle impacts, high stacking loads, and environmental exposure.
Okay, that makes perfect sense for, say, custom parts or small batches.
Right.
But here's the critical question for logistics. If we're talking about making millions of standardized crates for bulk use, doesn't 3D printing still lose out economically to traditional high-volume injection molding, even with the material savings?
That is a crucial point, and it's really the current frontier. For purely standard, basic crates, traditional molding does still dominate volume manufacturing.
Yeah.
However, 3D printing wins on two big fronts. First is rapid prototyping and verification. Manufacturers can print test crates really quickly to verify the AI design works before they commit to a massive, expensive tool-up. That accelerates the time to market drastically.
And a second friend.
And second, and maybe more importantly, it wins on customization and performance. If you need a crate that's perfectly contoured for a very high-value, fragile engine part, 3D printing is the only economical way to make that perfectly balanced, lightweight structure that protects that asset way better than a generic molded box ever could.
That flexibility is a huge advantage. So let's transition now to these so what. If we look across the whole supply chain, what are the, say, 5 big transformational benefits that these crates actually deliver?
The first one, and we've touched on this, is the pure financial win. A dramatic reduction of transportation costs.
The bottom line.
The bottom line. Less dead weight across your whole fleet means immediate, measurable fuel savings. This isn't theoretical. It's just money straight back into the company's pocket and a visible cut to their carbon footprint.
And beyond the money, let's talk about the operational side. That's our second benefit. Improved handling and efficiency. How does a lighter crate actually change the day-to-day work in a warehouse?
Well, think about warehouse automation. Your automated guided vehicles, your robotic arms, they're often limited by how much weight they can safely lift and move.
Right.
A 30% lighter crate lets those systems work faster, maybe carry more items at once, and use less power. That boosts your overall warehouse throughput. And for the human workers, lighter loads mean less strain, faster manual processes, and a huge cut in the risk of workplace injury. The whole process just gets smoother and faster.
Our third benefit is one that really speaks to modern consumer demands: material efficiency and sustainability.
Absolutely. When you remove material through optimization, you are inherently minimizing waste. The production process itself uses less raw material, which is a massive environmental win. This whole approach, only using what you absolutely need, is becoming non-negotiable for large global companies.
And that versatility we talked about, the unique strength of 3D printing, brings us to benefit number 4, high customization.
This is so critical for specialist industries. Imagine an electronics manufacturer that needs to transport these highly sensitive, really oddly shaped components.
Okay.
They can now get crates specifically engineered to cradle that unique shape, which minimizes movement and potential damage. Or they can be designed to interface perfectly with specialized loading equipment. That level of functional versatility was just impossible before, or way too slow to be practical.
And finally, we have to come back to that paradox again. The 5th benefit is enhanced durability. How can something that's lighter actually be stronger?
Because strength isn't about bulk. It's about intelligent reinforcement. The AI identifies the high-stress areas, the corners, the points where a forklift blade might hit, and it only adds material there.
Ah, I see.
The material that gets eliminated is the stuff that offered little to no structural help in the first place. By concentrating the material strategically, the overall structure maintains or can even exceed the protective power of a heavier, inefficiently designed solid crate. And that leads to fewer damaged goods and a longer life for the crates themselves.
And this isn't some far-off future technology. We're already seeing major global players adopt this. What are some of the current applications driving this change?
Early adoption is definitely strongest in high-value, high-precision sectors. So automotive companies are using these lightweight custom crates to transport critical vehicle parts. They're cutting transit damage and fuel costs at the same time.
Makes sense.
Electronics manufacturers are relying on that perfect fit and enhanced durability for their fragile products.
And I imagine the huge retail and distribution giants are getting involved, since supply chain efficiency is their entire world.
Absolutely. They're using optimized crates to streamline their distribution centers, get faster processing times, and critically, to prove their commitment to reducing our overall carbon footprint. This technological combination is becoming the standard because it really is the only thing that solves logistics' most persistent challenge, that balance between bomb-proof durability and minimum weight.
So as this technology matures, and the AI gets even better at understanding complex material properties and predicting real-world stresses, what do you see as the next step, the next innovation?
I think the systems will become self-improving. Imagine AI models that don't just design the perfect initial crate, but then they continuously monitor the lifespan and the failure data of those crates out in the field.
So they're learning in real time.
They're tracking exactly where a crate cracks or fails after 50 trips versus, say, 100 trips. This real-time feedback loop lets the algorithm instantly generate a version 2.0 that's even more efficient, even more robust. It leads to this constant, accelerating push towards smarter, more sustainable supply chains.
That's a phenomenal deep dive into how AI-driven topology optimization and 3D printing are just fundamentally rethinking how we use materials and logistics. They're driving cost savings, efficiency, and sustainability by making the humble crate a whole lot smarter.
And that leads us to our final thought for you to explore, one that moves a bit beyond the supply chain. If these AI algorithms can continuously learn from the stresses, the material fatigue, and the operational failures of previous crate designs to improve the next generation of tools, what are the broader implications? What about for designing permanent, large-scale infrastructure? What if buildings or bridges or even wind turbine foundations could learn and self-optimize their structural geometry based on decades of real-world operational data and environmental stress? The whole concept of a dynamic, continuously learning design could soon touch every single facet of the world we build around us.